Good morning. My name is Molly Shook, and today I'd like to present on tidal stream power. There are 321 million cubic miles of water within the oceans. That's 97% of Earth's water flowing in the oceans. After taking this course, you might see that as not just water, but as potential energy. So, how can tidal stream power help us access that energy? That's the question I hope to answer during this presentation. Before we can understand tidal stream power, we must first understand marine energy. Marine energy doesn't just come from the ocean alone, but from our oceans, rivers, lakes, streams, and numerous other bodies of water. The energy itself is generated by waves, tides, free-flowing water, and even changes in salinity, pressure, and temperature. There are various marine energy technologies used to capture this energy, such as barrages, buoys, fences, turbines, kites, and more. Unlike marine energy, tidal stream power refers specifically to, you guessed it, tides. So, what causes the rise and fall of tides? They're caused by gravitational interactions between the sun, earth, and moon. The moon's gravity pulls the earth, and because water moves more freely than solid ground, it begins to swell towards that pull. On the other side, the Earth's own gravity creates a force that pulls the water towards it as well. As the Earth rotates, our beaches go in and out of the gravitational pulls, and that's how the tides are created. One of the main advantages of tidal stream power is that it's not only renewable, but it's also very predictable due to the predictable nature of the tides. Tidal stream power also excels when other renewable energy sources decrease. At night and during seasonal dips, tidal stream power is often at its most powerful, unlike solar and wind sources, which have unpredictable declines. Another benefit of tidal stream power is that nearly 40% of the U.S. population lives in coastal communities. These communities are right next door to the vast renewable energy source that is the ocean. This would allow tidal stream power to aid rural and remote communities that currently rely on expensive shipments of fossil fuels and other forms of energy. And tidal stream power isn't just an idea that scientists and engineers have thought about. Technology has been effectively constructed and put to the test for many decades in various parts of the world. One example is the Lorentz tidal power station in Brittany, France. It's one of the largest capacity tidal power stations in the world and utilizes barrage technology similar to that of a dam. This type of technology works best when there is a very high tidal range and a narrow bay area. The power station was constructed in an estuary of the Rance River, which is a great location for this type of technology due to its high tidal range. The tidal range is the difference in height between high tide and low tide, and it's this difference in height that creates the pressure needed to generate power in a barrage. This technology uses small turbines and sluice gates to control the water. During the flood tide, the turbines are locked so that no water can enter. The gates remain open, allowing the water to rise on one side of the barrage. After the water has risen, the gates are closed and the turbine is opened to allow the water through. The water then spins the turbine and generates electricity, which is transferred to the grid. The Lorentz tidal power station has a peak rating of 240 megawatts, which is generated by 24 turbines and supplies nearly 2 million people with power. There's also a similar tidal power station in South Korea that produces enough energy to replace nearly 860,000 barrels of fossil fuel each year. Aside from tidal barrages, I believe there are two types of tidal energy technology that have even more promising futures in the world of renewable energy. Those two technologies are tidal stream turbines and tidal stream kites. Throughout the remainder of the presentation, we'll dive into these devices and discuss their advantages, disadvantages, current research, and overall concepts. I'll give you the bad news first. Tidal stream environments aren't just important for renewable energy, but they're also used for foraging and breeding by fish, invertebrates, marine mammals, and seabirds. Tidal stream technology could impact marine life. Changes in habitat may even cause some species to move away from the area, and so far, research on collision risk between turbines and kites with local species has not been greatly conclusive. Marine animal navigation and communication could also be impacted due to the underwater noise created by the turbine and kite systems. This may cause displacement in some sensitive species that avoid the electromagnetic fields altogether. Lastly, suitable locations for effective tidal energy are limited. Among those limited locations, some are not near the grid and would require substantial investment to install lengthy undersea cables for transmitting. We'll touch on some other obstacles later on in the presentation, but let's move on to the good news for now. Because water is over 800 times denser than air, tidal energy is more powerful and concentrated than wind energy, producing exponentially more power at the same turbine diameter and rotor speeds. As I mentioned earlier, the main advantage that sets tidal stream power apart from other renewable energy sources is that it's very predictable. Using a method called harmonic analysis, tides can be calculated. The National Water Level Observation Network uses engineered systems to detect and record changes in water levels, which are transmitted by satellite every 6 minutes. This allows for easier integration within our electric grids because the energy can be timed and predicted in advance. I also mentioned previously that tidal stream power excels when other renewable energy sources decline. At night and during seasonal dips such as winter, solar power isn't as abundant. Onshore wind also tends to blow more during the day than at night due to the heating of air above land causing pressure changes that create wind. So, what technologies can be used to harness this predictable tidal stream power? Let's look at tidal stream turbines first. Didn't we already create these on land? The answer is yes, but there are some surprising differences between wind turbines and tidal stream turbines. Tidal stream turbines are installed in areas with strong tidal activity, and they work well on the seafloor both individually and in arrays. They capture mechanical energy from the current, and underwater cables transmit that energy to the grid to produce electricity. These turbines vary in design, but the most common are breeze turbines, like you see on the left, and floating stream turbines, like you see on the right. So, what kind of research is taking place for tidal stream turbines? Let's look at the MyGen project located in Caithness, Scotland. The MyGen project seeks to evaluate the commercial feasibility of tidal energy and answer environmental questions related to tidal energy. The turbine technology used for MyGen consists of four 1.5 megawatt turbines which are affixed to the seabed with a tripod. The turbines are connected to an onshore power conversion station using a subsea cable, so tidal energy is exported straight to the national grid. All in all, the MyGen project has been successful and has created enough energy to power nearly 4,000 homes in 2019 alone. The project looks to expand and build out to achieve a capacity of 398 megawatts. More research on tidal power is also being conducted through the Orbital O2 turbine in Orkney. Those at Orbital have a strong focus on battery storage. The characteristics of the turbine allow Orbital to predict how much power it will produce and allow for storage and production planning based on those predictions. The turbine, which has been in operation since 2021, is 74 meters long and consists of two 1 megawatt turbines. Similar to MyGen, the O2 is connected to the electric grid through subsea cables and greatly aids in decreasing CO2 production. The O2 has also been largely successful and is scalable. The platform and blade can support sites with various characteristics and sizes. This is really important when looking at the commercial future of this technology. Now let's look at tidal stream kites and what they bring to the metaphorical energy table. Tidal stream kites are intended to produce electricity in tidal streams and ocean currents. They do this by moving in a figure-8 motion perpendicular to the ocean's current. As the current increases, the speed of the kite increases along with the energy production. So, what sets kite systems apart from other tidal stream technologies? The flying movement that happens under the water. The electricity produced by the generator in kite systems is several times greater compared to stationary turbines. The kite movement accelerates the water passing through the attached turbines at a higher rate than the actual current velocity, and this makes it one of very few technologies that might be able to exploit low velocity tidal areas and ocean currents. One application of this kite technology is Ministo's kite system in the Faroe Islands of Europe. As mentioned earlier, the Ministo kite system generates electricity from tidal streams and ocean currents through the use of hydrodynamic force created by the underwater currents. This force moves the kite, and an onboard control system steers the kite in a perpendicular figure-8. The turbine is pulled through the water at a rate several times higher than the actual current speed. The turbine shaft turns the generator, which outputs electricity to the grid through a power cable inside the tether. Ministo prides its technology on being lightweight, modular, and scalable. Another application of this technology is Sea-Power's Gemstar project, created in Naples, Italy. Gemstar consists of two counter-rotating turbines which are mounted to the side of the structure. The entire structure, which is held at the desired depth by a tethering system, is capable of aligning itself to the flow of the water. Like the Ministo technology, Gemstar behaves like a kite that remains fixed through a constant balance between the turbine thrust and buoyancy force in the hollow portion of the structure. Gemstar is claimed to be strongly competitive in the market. This is in part due to the single-point mooring system technology, which increases the number of suitable installation sites worldwide through overcoming difficulties faced by traditional installation. Projects like these can create learning opportunities for risk and uncertainties, which in turn help developers move projects forward into the commercial phase. Now that you've seen some promising research, let's discuss the obstacles that researchers are still working to overcome. First, the ocean motion is chaotic. If you've ever been on the beach vacation and swam too far out in the water on a yellow flag day, you can attest to this. Ocean waters don't just move in one direction, but heave up and down, surge back and forth, and circulate. This makes movement a bit more challenging to harness compared to the more straightforward movement like that of a gust of wind. To combat this challenge, new technologies are being created that are highly flexible and tailored to the chaos of the ocean waters. The ocean is also highly corrosive and destructive. Devices have to withstand harsh conditions while also being cohesive with the environment and habitat. Marine life could also be negatively impacted by tidal stream technologies. As I mentioned earlier in the presentation, changes in habitat and underwater noise can negatively impact marine life, and there is also a risk of collision with underwater technologies. A study published in the Journal of Applied Ecology also looked at how suspended particulate matter could help determine the overlap between energy devices and fish schools. Because suspended particulate matter scatters and absorbs light, changes in particulate matter distribution could impact species that rely on that light. For example, the vertical migration of zooplankton relies greatly on light, so if the particulate matter is disrupted, it could change the organism's migration pattern and impact not only the organism, but also its predators. I know this can be a bit confusing because each small change creates another small change and so on. Because of this chain reaction type of effect, technologies should be further researched and evaluated to reduce their environmental impacts. And lastly, and possibly the greatest challenge of all, is that tidal stream power must be made commercially feasible. Developing the tidal stream technology and connecting it to the power grid requires costly engineering and manufacturing that's still in the early stages of development. Researchers are looking for a way to capture and convert energy into usable power on a large scale and ensure that the costs are feasible. The industry is young and in need of an established supply and manufacturing chain. In conclusion, I believe the tidal stream power has a very promising future. With 321 million cubic miles of water in the ocean, tidal streams and ocean currents are not only reliable and predictable, but they're inexhaustibly renewable. Through more research and funding, new technologies and methods could be created to lower installation and maintenance costs, reduce environmental impacts, and increase the suitability of more locations. With emerging projects similar to those at MyGen, Orbital, Ministo, and Sea Power, renewable energy and tidal stream power could very well be the future of the world's energy. Here are the sources that I used for this presentation. I hope you enjoyed this presentation. Thank you for watching.